So we'll get started with the keynote session. Good evening, I'm Michelle Cat, and it is an honor for me to introduce our keynote speaker, Professor Greg Hager, who is the Mendel Bellman Professor of Computer Science at Johns Hopkins University and the founding director of Malone Center for Engineering in Healthcare. Professor Hager's research interests include computer vision, vision-based and collaborative robotics, time series analysis of image data, and applications of image analysis and robotics in medicine and in manufacturing. Professor Hager has served on editorial boards of IEEE TRO, IEEE PENI, IJCV, and ACM Transactions on computing for healthcare. Professor Hager has received many best paper and poster awards at various conferences. He is a fellow of the ACM, the IEEE, AAAS, the Kai Society, and AIME. Professor Hager is a co-founder of Clear Guide Medical and Ready Robotics. The title of his keynote is Computer Vision for Surgery. Let's welcome our keynote speaker.
Thanks, Michelle, for that introduction, and thank you all for coming to the keynote session. One thing I'll point out, you probably noticed the screen is a little, the image is a little small on the screen, so if you want to get all the excruciating detail and you're sitting way in the back of the room, you might want to consider moving up a little bit. I know no one ever does that, but I'm still trying to help you out here. So it's really going to be fun for me to give you this talk. This is work that we have been doing really over the last 20 years at Johns Hopkins. I came to Hopkins really just about 20 years ago. I was somebody who really was doing computer vision and robotics at the time. I didn't have any sort of background in medicine. I came to Hopkins and I was immediately pulled into a center on computer integrated surgical systems. It's led by Russ Taylor, and that's at USC. And the neat thing about that center was that it was trying to bring together clinicians, primarily surgeons or interventionalists, with the goal of trying to understand how can we connect technology to surgery. And so within the first year, instead of thinking about robots manipulating objects, I'm thinking of robots in surgery looking through microscopes and looking through endoscopes and trying to understand how we could make surgeons better in the process. So a lot of what I'm going to tell you about is really kind of the experience I've gained for those 20 years. I will say it would be tempting to give you the monologue memoir of everything we've done, but I'm not going to do that because, as I'm sure you've guessed, the last few years, the advances in computer vision, particularly deep learning, have really changed a lot of things. A lot of things we did 10 years ago really have been superseded. So instead, what I'm going to try to do is to kind of give you a little bit of a flavor of what it's like to work in this field, and how do you think about problems between medicine and computer vision. Just to whet your appetite a little bit about this, I thought I'd start out with a few questions. So the first is, in the US, how likely are you to have a surgical procedure in your lifetime? When you think about it, I mean, many of you are young, you probably don't think about this too much, that somebody can have surgery. But if you think about it now, you think it's 50% chance, 75% chance, it's never going to happen to me that something happens to other people. I don't know, how many people think you got at least a 50% chance of getting surgery in your lifetime? About 50% of you, in fact. There you go. So the answer is, well, if you think about all different types of surgeries, there's open surgery, there's minimally invasive surgery. There's also surgical procedures that are referred to as image-guided surgery. They don't really open you up, but they still move things in your body. Those are all interventional procedures of some sort, typically done under either visual or image guidance by a surgeon. If you look at that class of procedures, it turns out that on average in America, the average American undergoes 9.2 surgical procedures in their lifetime. About 3 inpatient, about 3 outpatient, and about 3 non-operating room invasive procedures, for example, biopsy. So the answer is probably all of you are going to have some type of surgical procedure in your lifetime, certainly in the US at least, and in fact you're probably going to have multiple surgical procedures in your lifetime. So it is most likely going to happen to you. If you look at just raw numbers, again, this is the eye chart, that probably is hard to see in the back, but so in the US, it's about 15 million surgeries per year. Worldwide, it's like a little over 300 million surgeries per year. Cost of surgery in the US, it's actually all over 200 billion at this point. Most interestingly, we're in a first world country here, obviously. We think of having access to surgery for whatever needs we have, but actually, a large part of the world actually lacks access to surgical care. There's a large number of deaths due to lack of access, as well as the inevitable complications due to surgery. So surgery is really a major public health issue, and it's a major public health issue in the United States, but it's a major public health issue globally. So let me ask you a second question. How important is the surgeon in surgery? So when you go and you have surgery, there's the hospital, there's preparation for surgery, there's post-operative care. The surgeon is in the middle of that. So how big a factor do you think the surgeon plays in all of this? I mean, obviously you're putting yourself in their hands, right? So here is a study done by Berkmeyer. What they did is they took videos of surgeons performing a standard surgery, bariatric surgery. They had an expert panel that reviewed these surgeries, and they ranked their assessment of the quality of performance, call it skill, on a scale of 1 to 5. And then after that, they correlated skill back to the patient outcomes. And I think you can see the numbers yourselves. What they did is they took the top quartile and the bottom quartile, and they said, okay, how much did our assessment of what the surgeon is doing affect outcomes of the patient? And so you can see readmission rates 2 to 3 times higher, reoperation rates 2 to 3 times higher, complication rates 3 times higher, mortality rate 5 times higher. Small, but still 5 times higher. So the surgeon plays a huge role in all of this. Now you might be wondering, well, what does one of these things look like? So I'm going to warn you, this is probably the one graphic sequence in this whole talk, but we are talking about surgery, so I think it's useful to see what does a surgical error look like. So I'm going to show you a surgical error. If you don't like blood in the insides of bodies, now's the time to check your emails, even if it's texted you, or something like that for just a few seconds. So here we go. This is a laparoscopic cholecystectomy. I want you to look for the error. Anybody see the error? Whenever you see green stuff coming out inside the body, that's a bad thing. That's scary. What's actually happened is that surgeon is doing a very standard procedure, laparoscopic cholecystectomy. Take out the gallbladder laparoscopically. And what they have done is they have to actually separate the common bile duct for some blood vessels and eventually do some dissection. And they just didn't quite visualize the bile duct correctly, and so instead of separating it, they decided to cut a hole in it instead. So they were now leaking bile. You see they're in there cleaning it up now. And that's going to be a major, so that's a situation where that patient's going to go from having a 90-minute outpatient procedure to having something more substantial to actually deal with that repair. Now you might look at that and say, oh my God, how can this kind of stuff happen? Well, how often have you been driving and you're driving along, you're doing the driving thing, and you're about to move left, and suddenly you notice there's a car in the left lane that somehow you didn't notice, right? That's about the sort of thing that's going on here. I mean, this is a surgeon doing a routine procedure, thought he had done everything right, there was a momentary lapse of judgment, perhaps, didn't visualize properly, and something like that happened. And so really the opportunity space in surgery is not unlike what we're seeing in the automotive industry today. You're taking something that right now is a purely manual process. It's the eyes of the surgeon, it's the hands of the surgeon, and what's going on in their brain, and saying, are there ways that we could augment what they're doing? Could we make surgery safer? Could we make outcomes better? Could we make the life of the surgeon better? And that's really the mission that we've been on over the last 20 years in my group and at Johns Hopkins, is saying, how can we support the surgeon so errors like that don't happen? Because it's better for the surgeon, better for the patient, better for the healthcare system if we can do that. So in this talk, what I'm going to touch on are a variety of different topics, but mostly I'm going to talk about how do we make the training of surgeons better, and how do we help them get better information while they're doing surgery. So we've done work in robotic automation, augmentation. So I'll say a little bit about that. It's in eye surgery. We've done a lot of work in using computer vision inside the body to do things like reconstruct and map out what's going on. We've done a great deal of work in training, and we're starting to look at also the process of surgery. The process, I'll just say, is interesting because I asked you how important the surgeon was. And I didn't show you a surgical error. But the fact is, surgery is a black box right now. You go into surgery, you come out of surgery. If you ever ask for the report of your surgery, it'll probably be about that long if it's a standard procedure. And it essentially says, I came, I saw, I conquered. I went in, I saw this sort of anatomy, I accomplished what I was supposed to accomplish, and the patient came out okay. It's not a lot of information about, well, I manipulated these structures, I did it this way, I saw these things. But really, that's the sort of insight, the lens that we need. And that's the lens that computer vision is able to give us, because anytime somebody's doing surgery, there's a camera there in minimally invasive surgery. There's a camera there that's seeing the surgical field. We can see everything that happens. And so that's really, again, the opportunity space in computer vision, and it's an opportunity space to start to think about the entire care pathway and what role the surgeon plays in. So let me start though by going back to really the core of what we've been doing, which is starting to first think about how do we support the surgeon, and in particular, how do we first understand the process of surgery so that we can do that. And so our starting point for this was really going back to the roots of how our surgeons train in the United States. So this is William Halstead. He's one of the 4 founding fathers of Johns Hopkins Hospital. He's an interesting guy. He actually introduced a lot of the modern ideas of medicine in the United States. Interestingly, I don't know if there's any, in fact, I know there are a few Germans in the audience. He traveled widely in Germany and Austria, and one of the things he was impressed by was the training programs that they had in Germany and Austria for medicine. And so he, in fact, brought that back, those ideas back to the United States. And it's what's commonly called see one, do one, teach one. Now, see one, do one, teach one doesn't mean you see a surgery and then you do a surgery and then you go teach it. It means you see a surgery over and over and over again, and it's what's called graduated responsibility or graduated ability. You slowly over time take over that procedure under the tutelage of a mentor. Once the mentor certifies that you are capable of doing that surgery, you can do that surgery, you continue to practice, you get more skilled, and now you can mentor the next generation of surgeons. So you see one surgery until you learn that you do it, and then you do that over and over again. But the fundamental idea is that you have to have a mentor there. So surgery is taught in this mentorship model. And so the limiting factor really is how often can you have somebody operating on a real patient with an attending there watching them, giving them a chance to practice their craft. So we started to think about, well, are there ways that we could gain insights first into what's going on in surgery and then eventually make it better. The real turning point in this happened in about 2000. This is the Da Vinci surgical robot. Many of you probably have seen it at this point, but back in 2000 as it was introduced, this was an amazing concept. What's happened is just remove the surgeon from the side of the patient and place him in a console. That console has a stereo video capability. The surgeon is holding on to a pair of manipulators that essentially record their hand movements and control tools then that go inside the patient. So really what this is doing is it's transporting the eyes and hands of the surgeon into the patient, but it's doing it with a computer in between. And since there's now a computer in between the video that's coming out and the surgeon's seeing it, and the tool movement that's going in, we can, for the first time ever, make a complete recording of surgery. We can see everything the surgeon saw, we can record everything that they did, and we can now start to make correlations between what they're doing and what's happening. So the interesting thing about this, when we first started, it was really just like phenomenal that we could get this data and start to work with it. Since then, it's grown to really be a standard of care in various areas of surgery. And in fact, just last year, Intuitive Surgical crossed the 1 million mark. So there were 1 million robotic procedures that were performed worldwide. So we really, in principle, now could get 1 million recordings of surgery. An incredible wealth of data if you could get your hands on it to start to learn what's going on in surgery. The challenge we were faced with, even in the early days, was we can get this data. I can make robots work for me by recording data. It's great. But it doesn't come with labels. I get lots and lots of data, but I can't get surgeons to sit down and say, well, right now, here is what I am doing. And so, in fact, not only could we not get labels, nobody knew what a label was. How do you actually even think about the structure of surgery? How do you think about what somebody is doing? And so this is the beginning of a project we call the language of surgery. And our theory, and this was backed up, of course, by talking to surgeons, is that there's a lot of preserved structure to surgery. When you learn surgery, it's not like you learn surgery A and then you wipe it out and you go learn surgery B, kind of like training a deep net, problem. But there's a lot of transfer. You learn suturing. Well, you reapply suturing over and over again. You learn dissection skills. You apply them over and over again. So there's a lot of preserved structure. So in some sense, if you can build the right alphabet of components of surgery, you can actually start to understand many surgeries using that set of components. And so we really focused on 3 problems. First problem is recognizing what's happening. Can we go through a surgery and can we basically read out, here's what's happening with the surgeon, and can we invent a language for doing that? And so, in fact, what we did, starting at a very fine-grained level, talking about the very basic components of surgery, and moving all the way up to the basic, the broad steps of surgery, as I'll show you a little later. Once you can recognize it, more interesting question, back to that Burkmark problem, can I tell you how well they're doing surgery? Wouldn't it be great if I could actually observe a surgeon and I could give them a scorecard that says, hey, relative to your peers, here is how you are doing at this particular surgery. And in fact, even better would be if I could take another step and actually give them some idea of how to improve their performance. There are surgical trainings. It is possible to say, right now, your suturing technique when you're doing a backhanded drive is a little bit inferior, it takes a little bit longer than college. You should go on a trainer and just practice that a little bit so that you have a better skill. Not unlike what an athlete would do if you realize that they had some sort of deficit. So we've been, as I said, doing this since our first publication, I think in about 2006. Since then, it has expanded to many, many areas of surgery. We do a lot of robotic minimally invasive surgery and minimally invasive surgery. So FES is actually minimally invasive surgery with sinuses. We'll see that later. Hysterectomy, prostatectomy, hernia surgery. We do a lot of work under a microscope. Stereo microscope is a great way to record video and understand what the surgeon is doing. So retinal surgery and cataract surgery, we've done work in extensively. You'll see some cataract surgery. And then septoplasty is our first open procedure where there's actually not an endoscope involved at all. The surgeon is working directly. And so I'll tell you a little bit about all of these as we go through the talk. First, just to again kind of get you engaged, I'm going to give you another little test here. When I first started to do this, people thought it was kind of crazy that you could teach a machine to quantify skill. And so what I'm going to, and what I used to do is to convince people it's not as hard as you might think. So I'm going to give you that quiz here. So you're going to see 2 surgeons, or 2 users of a Da Vinci robot. You see it's just a benchtop task. One of them is a practicing surgeon, and the other is somebody who's actually used the robot a little bit, but they're not a surgeon and they haven't practiced this task. Your job is to basically raise your hand when you think you've figured out who is who in this video. All right, so here we go. Oh, and I've synchronized the video, so timing is not really a clue. There's kind of these different stop points where we make sure the video is time synchronized. So here we go. Just raise your hand when you think you know who's good, who's bad. It was the best of times, it was the worst of times. Okay, I can tell from the chucks and nodding too, you need to raise your hand anymore, right? It's pretty obvious. Can anybody tell me what they're doing wrong? Why are they so bad? What do you think?
Their ankle twisted off when they're trying to push it through.
Terry got it. Terry's pretty surgeon. They picked up the needle wrong. The reason that they're having so much trouble is, if you noticed at the beginning, the expert surgeon who's on, I think your picked the needle up, the first thing they did is they adjusted it a little bit. They set themselves up for success, which is what surgeons often talk about. The person on the right just grabbed a needle and started going. And, well, you can kind of see how this goes. So it's not that hard to see, right? You can see the difference in somebody who knows what they're doing and not doesn't know what they're doing. This is what happens if you look at the tool trajectories in those 2 plots. So you can see the person on the expert on the left, 4 perfectly placed suture throws, And what we've done is we've color-coded them by this basic model, this basic language we use to describe surgery. Right, you see the non-expert, they're getting the task done. But clearly there's a lot less structure to it. And interestingly, if you start to look at how they're using this basic vocabulary, you start to see something like this. So an expert, very efficient, very linear. In fact, I happen to know who the surgeon is. He was a beta tester for Da Vinci, so he's kind of a robot himself almost. But he just uses a robot that does the same thing every time. And you can see the novice, of course, is all over the place because they're going back and forth and kind of trying to fix things. What's interesting is you can take these representations, and we showed this in our first data sets, and you can collapse them down. Just pick your favorite dimensional reduction tool. And you can actually start to see a space of skill and an evolution of skill. So in this diagram, green, you can see it from the way back, is novices. You can see there's a big, wide envelope of novices. That's because every novice is a novice in their own unique way. They all find different ways to be bad. But as they practice, they actually start to focus down. And if you look, the intermediate, which is the blue, the blue is intermediate, so they've started to collapse, and you can see the experts are actually, in fact, very tightly clustered. So experts, you just have to look at them, actually look very, very similar. Everybody kind of converges to the same theory. So this was like our first, hey, wow, there is something here. We can actually start to see people's learning evolution. Now you might say, well, but that was just a benchtop task. That was a cartoon, and we had a surgeon, and this isn't real. And well, whatever you make up, I've heard it. So don't feel bad if you're thinking about it. So what we said is, well, okay, can we replicate this in gravity? So I mentioned that procedure septoplasty earlier. What's septoplasty? It's basically a part of correcting a deviated septum. Correcting a deviated septum, this particular procedure is what's called an index procedure, meaning that if you are a resident in surgery, you have to do this procedure. You have to be evaluated on it. In fact, so it's a big funnel area. Everybody goes through that procedure. So it's a great place to see both attendings doing it and see residents do it, see residents in all different levels of skill. So the way we do this is we actually attach an EM sensor to the tool. It's called Cabo. And we record their motions, like we recorded with the robot. There's no endoscope in this case, no video, so really the video you're seeing here is just more for us to know what's going on. But you see on the left is a novice. It's actually a first-year resident who's in there for the first time, just trying to learn how to do this procedure. And right, you see the expert, you can see a very similar sort of structure emerging, right? The novice is not efficient, they're going back, they're going forth, it takes a long time a lot more movement to do this procedure. The expert, very efficient. And in fact, if you do the same sort of dimensional reduction, what's happening, you can actually start to plot the same sort of skill trajectory that's happening. And what we've done here is we basically plotted the distance from the kind of average novice, if you will, and the distance from the average expert. And so they start out close to the novice and further from the expert, and as they evolve, you see they start to fall more into the gravitational well of the expert side of the diagram instead of the novice. And so this really does exist. This is something that you can actually start to think about doing repeatably in surgery. So this is all fun, this is all great. You might be sitting there now saying, well, but we are at a computer vision conference and you just said there was no camera in this, so why are you talking about it? So if you're thinking that, the next step is to say, well, can we do this kind of stuff in video? And again, up until maybe 5, 6 years ago, it didn't really seem like something was feasible, and furthermore, we didn't really have the data sets to do it. But in the last few years, we've started to embrace it. We didn't start with skill, though, and the reason we didn't start with skill is because, again, it comes down to data sets. How big a data set can you collect, and how well can you actually get ground truth labels for that data set? And it turns out, we'll see an example later, but skill is a little harder to do that with. And so we started with something else. We started with what's called surgical phases. So when you do a surgery from beginning to end, a surgeon naturally thinks of a set of steps. You have to enter the body, you have to expose the anatomy you're interested in, you manipulate that anatomy, and so on and so forth. And the neat thing about this is that it's not super hard to get them to label that because there's a kind of standard nomenclature for this. And they're reasonably consistent about it. And furthermore, you can think of this as being one label per frame of a video as opposed to something like one label for a video, which is what scale is. So that's why we started with phases. And it actually helped that there were groups, and this happened to be a group at TU Munich, that started to put together a data set around surgical phases just to kind of spur a competition in this space. So we're going to talk about phases to start with as a way to get into the problem. Now, so the good thing is that it's a very well-structured problem. This has to be cholecystectomy again, gallbladder removal. It's a linear process. As I said, we can kind of get a pretty consistent set of labels. The problem is that it's still the case that you can see a lot of variation in this, with variations in the appearance of the patient. So on the left you see somebody who's an obese patient, on the right somebody who's not obese, as well as the fact that everybody does a little different. Interestingly enough, one of the first things we started to realize as we started to look across these data sets is that different institutions have different models for how procedures are performed. We can actually start to identify clusters of individuals by basically their workflow, how they do the procedure. So this is where we were a little bit challenged. But we looked at this problem. This is really the work of Colin Lee, a student of mine who finished a couple of years ago, where what we realized is we needed to somehow develop a method that could somehow capture both spatial and temporal features of what was going on. And we had to be able to do it in a relatively low data set. You know, again, we're not going to get 1 million surgeries and train on it. We're not going to get the labels for 1 million surgeries and train on it. And so the idea was to really combine two types of convolutional methods. So we call this temporal convolutional networks. The first step was to say, well, we have a label per frame. Let's just try to first train something that tries to extract the phase label just from a static frame. So we can train a CNN to do that. We're going to get a feature vector. And now let's just take those feature vectors as a time series, and we're going to put a convolutional network on top of that that's basically going to process that temporally now, and is trained separately to actually do the labeling itself. So we did this on our cholecystectomy data set. This, of course, is, again, at a time when CNNs were still kind of coming into wider use, so this was really kind of the first time we had tried this sort of approach with video. What was interesting about it is, so we basically took a VGG-like architecture, we modified it a little bit for our spatial component. And once we did that, it's interesting, if you look at the index of max filter down here on the left, you'll notice that it's actually doing a pretty good job of segmenting the tool. And as we started to train the system, we realized that it pretty naturally started to segment out a lot of things that actually made a lot of sense to surgeons, like the tools. It's actually segmenting out the gallbladder separately from the liver. It's actually extracting the sort of information that we would actually expect as the context for doing this. As I said, on top of that, we put some temporal convolution, so now we can scan across and put together some time series information. And to just cut to the chase, how well did this do? Well, actually, it did quite well. So we were able to show, for video, we could get about 85% accuracy. What that means is, if I give you any frame of a video, 85% of the time, you're telling me the right phase for that video. And in fact, this is a little bit pessimistic because there is some, it's not quite clear when one phase ends and another phase starts off. And so if you add like 30 seconds of delay, you can get that number up to about 90 seconds, or 90%. But the interesting side effect of this, though, is we also had the tool motion from the Da Vinci robot. So we could say, well, what if we tried to do the same thing from the tools? And it turns out just using tool motion gives us about 90%. So tools actually beat doing all the video processing, just knowing what the tool is doing. You can see that the deep net is kind of trying to learn what the tool is doing, so it's probably using similar information. And in fact, you can see that's true because if we put tools and video together in time series, we only get another percent or so. And so the first order really is the tool information, the tool motion that it seems like the deep net is focusing on. But nonetheless, we were super pleased that we were actually able to get, straight up from video, this sort of result, because cholecystectomy often doesn't have a robot there. You can't actually record the tool movements in a typical case. So this was great, but one of the challenges here, or one of the elements of this result, was that it was on this data set that we got from TCNS. Well, it turned out that was a data set that was reported at a single university hospital from a very small number of surgeons. And so one of the things we wondered was, well, how well preserved is this result if we start to look at a more representative population of videos? So a student colleague lady went out and said, you know what, it turns out if you go out on YouTube and you just type in laparoscopic cholecystectomy, there are a lot of surgeons that like to upload their highlight reels. So they will upload their laparoscopic cholecystectomy for you. And furthermore, they do it around the world. Surgeons in India like to upload their best surgery, and surgeons in France like to do it. So we actually collected videos from YouTube, 19 hospitals, 12 countries, and we said, okay, what happens when we train our system up and we try it on those? And I think you can see we don't do nearly as well. And that's because, of course, the original data set we had was just too small. So you might start to ask yourself a question. Well, how much do we need? So I said that we could get 1 million videos. 1 million might be enough. I mean, a lot of us like to make 1 million videos these days. This was under 100 videos. Under 100 videos is not enough. I mean, the average surgeon has to practice about 200 times to get the surgery right. So you kind of like to think the deep learning system maybe at least 200 cases. So we don't know the answer for sure yet, but I just highlight some of where this work is going. This is a company called Theater.io. They just started up a year or so ago, and they're basically trying to take this sort of approach using computer vision straight from laparoscopic video, upload to their server. They do all of the face labeling. They actually label some events, and what they can now do is they can follow the entire time series of surgery. So they will. I can't give you precise details, but let's say they have north of 1,000 videos, and they're using the most recent methods you might imagine apply to time series video data, and they're getting north of 95% reliability, and they're doing it on videos across the world. So it seems like the answer is probably somewhere a little over 1,000, but it's probably not 10,000, is enough to actually start to get a machine to be able to reliably recognize what's going on. Furthermore, once they do this, you can actually start to do some of the things I talked about earlier. I can give you a scorecard for every surgery. So I now know the analytics for whatever surgeon did in surgery, and I can compare them to whatever cohort you want to compare them to, and say, hey, you took longer in this phase, you took less long in that phase, and so on and so forth. So, it's happened astonishingly quickly to me, but in the last 2 or 3 years, suddenly we've seen actually 2 or 3 groups pivot, and they're now starting to say, how can we actually use this in real practice in surgery? And we're actually starting to see data sets grow, and we're really at the beginning of a wave of starting to get the sort of analytics that will let us provide that next in the surgery. So that was the story of phase, and I set this up by saying, well, we did phase because it was kind of low-hanging fruit. It was easier to do. We could get the data, we could get the labels. But I was really talking about skill. So can we do skill growing video? Skill seems like a harder thing to do, right? Because you've got to summarize something in a more abstract way. And we know we can do it from the tool movement data again, but we kind of know what to summarize in that data as well. So we actually did an experiment recently. So this is a cataract surgery, and it's actually in one phase of cataract surgery. It happens to be a part of the surgery called rexus, where you're actually preparing the eye for the insertion of the new tassel, the new lens. So what we did is gathered a set of videos, and we crowdsourced all the tool information, the same information you saw before, so we can actually do skill analysis using tool information. But we also computed optical flow, ended up being the best signal. We tried a lot of signals, but we're going to stick with optical flow as the best on the video. So you can think of having 2 time series. One is what tool's in the eye and how's it moving, and the other is I'm going to give you optical flow and We use TCNS again, a little bit of a modification. We add essentially a time series component that summarizes the whole video, a little bit like an RNN. So we end up with a state at the end that we can then project into a skill label. And we have 99, not 100, 99 videos of capsule rhexis that we captured. We have a surgeon who is really interested in this work, and she has just been super to do this. She also managed to get her colleagues to apply skill labels to these videos. I just want to say a little bit about that. One of the things I have learned is you would like to think that surgeons all agree on what skilled means, and it turns out that they do not. So in fact, one of the things that we've had to do, kind of like learning, figuring out what the language was to describe surgery, we've had to figure out a mechanism whereby we can essentially get a consensus skill label. You can't think of this as ground truth. You can kind of think of this as their best guess as to what the right skill of this person is. So we're never going to get to 100% because surgeons never get to 100%. You get surgeons to agree 90% of the time on this, you're actually doing really well. So in any case, we've got to label all this, we've got to go through this consensus process, and we define really just a binary classification, expert versus novice. The idea being that there is, they rate them on this scale, and if they rate highly on a couple of steps, we'll call them an expert, and if they don't rate highly, we'll call them novice. So it's a, again, it's a grayscale, and we binarize it. And the answer is, so you can extract skill from video. If you, let's see here, FF is optical flow, and so we're better than chance, 63%. But if you look up here, this is tool velocity. You can see that we're actually up at 85%. So we still haven't been able to crack the skill nut with video yet. Now, whether that's because the data set is too small, whether it has to do with the techniques we're using, I really couldn't tell you. But the fact that we can actually get already some signal out suggests to me that there is a lot of opportunity in this space. And I think what it's really waiting for, back to what I said before, is a large enough data set, something that's in the hundreds or thousands. And I think we're actually going to be able to start to judge more accurately skill of surgeons in video. So that's kind of an abbreviated story of language surgery. I could go on. We've done many other kind of elements of this, for example, going on and saying how do we teach surgery, how do we actually recognize what they're doing wrong using content-based retrieval and so on and so forth. But I kind of figured by this time we would get tired of this story. So I want to shift gears just for the last few minutes and kind of give you a different perspective on how computer vision can impact surgery. Right now, everything I've talked about has been all about essentially fine-grained activity recognition. Can I recognize what the surgeon is doing and how well they're doing it? But the fact is, they're doing it to anatomy. And I haven't said anything about, well, how do you actually ground all of this in what they're actually working on? And so I'm going to say a little bit about some work we've been doing in this space, really building systems that give them better awareness and understanding of anatomy, again, in this realm of understanding what's going on in surgery. So I call this navigating inner space, because really what we're doing is we're using cameras inside the body to navigate and see what people are doing. So I'm going to also shift to a big part of the body and then move to the head. This is endoscopic sinus surgery. And I'm going to focus on what's called functional endoscopic sinus surgery. If you have a stuffy nose all the time, you have trouble breathing, you have nasal obstruction, and it never goes away. You know, it's not that you just have a cold or anything like that. It just, you always have trouble breathing. Ultimately, you will go in for surgery. And that surgery essentially is removing some of the bony structures inside your sinuses. Your sinuses are a series of cells that have, actually they evolve as an embryo in kind of a stochastic manner. But they do have kind of a preserved structure to them. And they go in and essentially remove these bony cells, they'll widen the sinuses. And in about 75% of patients, this actually alleviates the symptoms. You come out and you're actually able to breathe more freely. There's about 365,000 cases of this per year in the United States. The key thing about this is it's done using what's called a surgical navigation system. So you know what a navigation system is for your car, right? You plug in a destination, it takes you there, and knows about the roads and everything else. Well, a surgical navigation system is a little bit similar. It's designed to allow a surgeon to visualize anatomy that is below the surface. So if you've got a preoperative CT, what you'd like to be able to do when you're looking through the endoscope is to correlate what's in the CT to what you're seeing in the endoscope. So for example, the carotid artery is actually very close. You see actually up here, you can read it. So this is the optic nerve right there, and that's a carotid artery down there. Those are no-fly zones for any surgeon. They want to know what those are. They can't actually see them in the endoscope, but they can take a pointer tool and point at it. They could look at the corresponding point of the CT and say, aha, as I move the pointer around, I can start to get a sense, this is where the carotid artery is, okay, I'm not going there. Here's where the optic nerve is, okay, I'm not going there. So if you put it in terms of transforms, the way that these systems work is they mount a tracker to the head of the patient, they mount a tracker to a pointer tool, they go through a registration process, and essentially establish a spatial relationship between the pointer tool and the patient in the CT. So now I can point it at a point on the patient, transform that, and that eventually ends up at a point on the CT. The interesting thing is, if you look at it, there's a very direct transformation that would let them visualize directly in the endoscope what's going on in the CT. It's this one. It just goes from the camera to the CT itself. And so you can think of this as the problem we call video CT registration. Could I put a camera inside your sinus cavity, take an image, correlate that image with the CT, compute the location of the camera, and at that point I can now visualize anything I want about that CT. And it's a beautiful computer vision problem because if you could do this all from images, it would radically change practice. So what are the challenges? Why would you want to do this with video? Well, there are a lot of reasons you want to do it. So the first is that navigation, as I described it, assumes a rigid body. It actually assumes that whatever you're operating on doesn't change while you're operating, which, if you notice, is a logical contradiction because the whole point of operating is to change the anatomy. So yes, when you start out, you can use it, but as you go along, you lose touch with the CT. Eventually, it becomes essentially useless because you change the anatomy, you don't know where you are. The second is it's only good about 2 millimeters. The bony structure that covers the carotid artery is less than 1 millimeter thick. So a surgeon of mine says it's kind of like navigating with Google Maps, except Google Maps is only good to a few blocks. So you put in a destination, you can kind of get there, but then you gotta kind of poke around because it doesn't give you the resolution to get down to the house. And the last is that navigation right now is only used when there's really a reason to use it. It could often be used in other procedures, but it's expensive, it's cumbersome, it takes time to set up, so people don't use it. Meanwhile, video, it's always there, it's cheap. We can actually show back to the envelope, it can be about 4 times as accurate as a standard navigation system. So we set off down this path about 10 years ago. And it started with Rick Zelinsky's paper, Snavely, Steve Zeitz, and Rick wrote this paper, I don't know how many of you remember it, taking lots of images and putting them all together in a big registered space and being able to now relate all these images to each other. So in my head, I replaced the Roman Colosseum with a sinus cavity and the cameras with endoscopes, and I said, this is my problem, I want to solve it. The problem is that the sinuses don't look a lot like the Roman Colosseum. You probably knew that, but here's a little bit more of what you see. It's not a feature-rich environment. It's not like looking at El Cap or Roman Colosseum or a house or something like that. It actually is very feature-poor. So we actually have managed to develop a system that does full surgical navigation. It required a lot of interest in computer vision engineering to get to the point that we could really get reliable structure from motion. Getting reliable structure from motion meant we could do a 3D reconstruction, we could do a 3D registration between the CT and the video images. But we really wanted to do more. This was not like a system that I would want to deploy yet. But of course, again, the last few years, with deep learning, a lot of other possibilities have come up. So, for example, the idea that you can do self-supervision to build depth maps. And so, would there be a way to go from the sparse depth map we're getting to feature matching to something that was dense, something that would really give me a fly-through? So my dream was always I could get a fly-through of the sinuses just from a video screen endoscope. And for years I would talk to students and I would say, this is what I want. And then we'd write papers on something that just wasn't quite there. And then just in the last year, we actually have for the first time gotten to the point I created about 10 years ago. And this really is due to my colleague Matthias Imberat and Jean Tom, one of our grad students. And they took really these two ideas, this idea that you can do structure from motion and sinuses sparsely, together with this idea of doing dense single frame depth estimation, and they actually put it together into a system that's pretty impressive. So just briefly, what do? They do structure from motion based on self-supervision. So, Siamese network process multiple frames, you get a depth map. But because we can do structure from motion as well, we actually know the coordinate transforms between the cameras, and we've reconstructed 3D. So we can actually do a full 3D flow between these frames, and we can use a depth consistency loss, a dense depth consistency loss to say, okay, we should be able to get all of these frames consistent with each other, assuming our poses between the cameras are correct, which we actually believe because we've got a pretty robust system for it. So what they added to it, though, is they said, well, look, from that structure from motion, we also know sparsely some feature points, and we know those feature points really accurately. We know them very well. And so we can add another loss that actually ties the depth map down to those feature matches. What it really does is it gives the network a hint. It says, look, in these places, you should get this right. We know exactly what right is. It's not just that you all agree, but you got it right. And when you put those two things together, you get a remarkably effective algorithm. So we actually have data that we collected from patients undergoing tests. We have video of those patients that we've broken down into areas of the sciences that we understand and can then compare to CT. We use fairly standard architectures, tweaked a little bit like everyone to get these things to work. If you want to go to GitHub and you can download it. The result is that we were, again, I apologize, it's hard to see with this contrast and in this resolution, but we get actually remarkably good results. Results that to the eye actually look very photorealistic when we recognize it back. And this is knowing nothing. We don't even use the CT at this point. All we're doing is we're just flying the endoscope through, learning essentially on the fly how to do the reconstruction and then pulling the reconstruction out. And in fact, we get almost exactly what I predicted way back when we'd be able to get from cameras. We get about a 0.5 millimeter accuracy. Should you care, a CT image is good to about a 0.5 millimeter. So we were actually at CT resolution using nothing but raw video. And in fact, if we go further, this was actually just reconstructing from a segment. What if we actually fly through and we just basically start to build a longer map of what's going on in the sinuses? We do this in kind of a unique way. We start out and we essentially video card our way as we go. So we're essentially producing a volume model that looks very close to the CT, which among other things means we can register easily to CT. And when we do that, we get even more amazing results. And so this was the result where a couple months ago I saw this, and after 10 years of waiting, I finally had a student who came to me and said, I've got a full video reconstruction of the sinuses that is accurate to CT level. And that's actually what you're seeing here is just a little snippet of it where we're flying along and you actually, the 3D geometry is changing. We're computing where the camera is. We can register that to the CT, and now we can do all the stuff that surgeon wants to do in navigation. But in addition, we've actually built a real live 3D model of exactly what the anatomy is, not what the CT said it was maybe 2 weeks ago. The accuracy isn't as high on this method, interestingly enough, but we think that's because we're now reconstructing over a minute of video as opposed to a few seconds. And in fact, if we look at the registration result, our registration result is far better than what we're getting in initial video sequences. What's actually interesting to me is not only are we solving a problem that exists, we're taking navigation and saying we could do this in a much more pervasive way, but actually the interesting piece of this is now when you go and you scope a patient in the clinic, which happens for all these chronic patients, you could actually build a 3D model. And if you could build a 3D model, there are all sorts of things you could start to do. For example, I don't know if you noticed, but I said that FEST was successful, what % of the time? 75%. That's not a very good surgery, quite honestly. How often do you want to go to surgery and say, well, 1 in 4 times you fail? I mean, luckily it's not die. I mean, obviously if it were die, you wouldn't do it at all, right? Why does it fail? Nobody knows. But one of the things they've never been able to do is to correlate anatomy of the patient to what the surgeon is doing to the outcome the patient gets. What we can start to do is we can start to build a population of shape models of patients who have different types of diseases, and we can actually start to look at what is the correlation between anatomy and outcomes. So you can imagine this. This is actually some work that we published recently. We built a shape model of the sinuses. This is a very straightforward PCA-based shape model, which means now we can index every patient we observe in a shape space. And now we can actually start to ask, well, you know, if I pick a couple of points in that shape space, are they more on the green side of things? Are they actually likely to benefit from the surgery? Or are they more on the red side of things? Is this a morphology that's not going to be amenable to surgery? Or is there a surgery that's better for them? And in fact, we've been able to show this for another failed surgery, spine surgery, which has a high failure rate, that adding this morphology actually does give us predictive ability. And so we really have the opportunity to start to think about really image clouds, as we start to think of them now, that we could use to study medicine, study surgery, study the effect of anatomy in ways that we never could before. So I know I'm running short of time here, so I'm going to just kind of say, you know, because of I'm being long-winded, I knew I wouldn't have time to talk about a lot of the other stuff I want to say. So I'm not going to tell you about robotic guidance, which is something that we're also very actively working on. We're actually doing this in eye surgery. A lot of groups are interested also in what's going on outside the patient. So this is Nicola Rosberg's doing some really nice work in surgical workflow analysis. And also he's been using this to study things like X-ray exposure for physicians. Raphael Stigman in Switzerland has really done a lot of incredible work on tool tracking. You notice that tool tracking, tool numbers seem to be one of the key things that let us be able to tell what was going on in surgery. Well, if we can track the tools, we can replicate that without having the issue there. And Raphael's well known way to do that. And this is, Vishal mentioned that I'm a founder of CurGuide Medical. This was actually one of the first cases where I really put computer vision in the real world. There's a pair of stereo cameras mounted on an ultrasound probe there. It's tracking all the tools that go in and out of the patient. And what it does is it provides on-screen guidance for ultrasound-guided procedures. So if you go to CurGuide Medical, you can buy a vision augmented ultrasound probe that gives you new guidance capabilities that did not exist before we put the company together. And what's interesting about this is it actually goes all the way back to where I began, because as we're using this system, we actually can start to collect data on how surgeons perform their job, and we can use those data analytics to start to study what does a good interventional radiologist look like. So that's probably a good kind of tie-up to say, you know, I think surgery is entering a world where for over 100 years it was a black box that was taught by somebody who was skilled at surgery and taught the next generation and passed that knowledge on, but we never knew what that knowledge was. And we're actually entering an era where surgeons themselves are getting incredibly excited by the opportunity to start to understand the structure of surgery, start to harvest data on it, not just to improve the quality of the work that they do, but to also understand how to innovate that to better improve the outcomes for patients. So I would say we're really just at the beginning, at the dawn of data-driven surgery. The opportunity space is huge. And since it's Super Tuesday, I thought I would say you should join the revolution and join us all in working in this space. So with that, let me just say this is the work of many people, my engineering collaborators at Johns Hopkins who are incredible, many clinicians at Hopkins who are just also heavily invested in this work in many ways. I want to call it the science team, particularly Ation who was the one who finally fulfilled my 10-year dream for the Phi group. Of course, our funding, and with that, let me end there and take a couple minutes of questions before we get to